Hello, good morning. My name is Dr. Rajkumar, Mechanical Engineering Department, GM Instructor Technology, Downville. This is a screencast video of open educational source from RC1176 UBDTC, Downville. So in this video we are going to discuss the basic concepts and definitions of turbomachines. The course we chosen from OER Mechanical and Allied is turbomachines. Our team members are Dr. Rajkumar DG, Mr. Madhukar Yudhri, Mr. Anasiddhaya. The introduction, we are going to discuss what is the basic definition of turbomachine. A turbomachine is a device in which energy transfer takes place between a flowing fluid and a rotating element due to the dynamic action that results in the change of pressure and momentum of the fluid. So here we are going to discuss about the rotor as well as the stator, and there will be change in pressure as well as momentum of the fluid. And based on this, we are going to classify three different types of turbomachines. In the first one, power generating turbomachine, power absorbing turbomachines, power transmitting turbomachines. So what do you mean by power generating turbomachine? So it is a one machine which converts fluid energy in the form of kinetic energy or pressure energy into a mechanical energy in terms of rotating shaft. Turbines are the best example for this type of turbine. This type of machine. So in coming to power absorbing turbomachine is one which converts mechanical energy into fluid energy. The best example for this is compressors, fans, pumps and blowers. Coming to a power transmitting machine is one which is used to transmit the power from driving shaft to driven shaft with the help of fluid. So in power transmitting machines from IC engine, so the power will be transmitted into a alternator. So the transmitter, here we are going to convert the mechanical energy into electrical energy. Coming to a comparison between positive displacement devices and turbomachines, there are 6 modes of comparison between positive displacement machine and turbomachine. Coming to action, it involves changes in volume or displacement of the fluid. That is for positive displacement machine. Turbomachine, it involves a change in pressure and momentum of the fluid. Coming to operation, positive displacement is unsteady flow of the fluid. So whereas coming to turbomachines, it is a steady flow of the fluid. Coming to a mechanical feature, because of reciprocating masses, vibrations are more in case of positive displacement machine. Based on the rotating masses can be completely balanced, the vibrations are eliminated. The efficiency of the conversion process, we are going to consider high efficiency because of static energy transfer. Efficiency is low because of dynamic energy transfer. The volumetric efficiency much below that of turbomachine. Because of walls, it is almost 100%. Fluid phase change and surging, no such serious problems are encountered. Causes cavitation in pumps and turbines, therefore leads to erosion of blades in case of turbomachine. The efficiency of a turbomachine. For a power generating machine, the efficiency is defined as the actual shaft work output to hydrogen energy available for the fluid. So the actual shaft work output what we have to consider, that is the brake power that is available at the shaft output. Hydraulic dynamic energy we are going to consider for the fluid inlet energy, rho q g to h we have to consider. So coming to a power absorbing machine, the efficiency is defined as which is the reverse of that of the turbines or power generating machine. So it is the ratio of ideal work input to the actual shaft work input. And coming to mechanical efficiency is defined as the mechanical energy supplied to the rotor to the actual shaft work input. So coming to a dimensional analysis, it is a mathematical technique with the dimensions of the quantities involved in the process. So we are going to consider fundamental dimensions, secondary dimensions, and dimensional homogeneity. So in the fundamental dimensions, MLT system, we have the mass, length as well as time. That is fundamental dimensions. By using the fundamental dimensions, we are going to derive the secondary dimensions. The dimensional homogeneity involves that left hand side of the equation must be equal to the right hand side of that equation. So based on that, we call it as a dimensional homogeneity. In this method, for reducing the number and complexity of experimental variables that affect the physical phenomena by using a sort of contracting technique. There are three repeating variables going to create bucking pi terms, pi terms in bucking pi theorem. So these three repeating variable involves one other variable from the generalized function relation. So first we are going to consider geometric variable, kinematic variables, and dynamic variables. The geometric variables involves length, diameter as well as height, whereas kinematic variables involves velocity as well as acceleration, and dynamic variables involves the fluid properties such as density, as well as kinetic variable density, as well as we are going to consider viscosity. So those properties, fluid properties, we are going to consider in case of dynamic variable. So coming to a pi terms. Coming to a pi term, the coefficient is defined as the specific capacity. The term cube divided by nd cube is the capacity coefficient, which signifies the volume flow rate of fluid through a turbomachine, unit diameter or runner operating at unit speed. The speed ratio, it is defined as the ratio of tangential velocity of the runner to the tangential jet velocity of the fluid. Coming to head coefficient, normally this flow coefficient Q by N Q, we are going to designate a pi 1 term. This is a pi 1 term in case of this terminations. So the term GH divided by N square D square, this term we call it as a head coefficient, whereas this Q by N D cube, this term we call it as a flow coefficient or specific capacity. GH divided by N square D square is also called as specific head. It is a measure of the ratio of fluid potential energy and the fluid kinetic energy while moving at the rotational speed of the wheel U. Coming to a power coefficient, the term P divided by rho n cube to pi is called power coefficient or specific power. It represents the relation between the power, fluid density, speed, and wheel diameter. For a given machine, the power is directly proportional to the cube of the tangential speed of the wheel. The specific speed is the dimensionless term and is parameter of greatest importance in any compressible flow machine. The specific speed is the only parameter that doesn't contain linear dimensions of the runner. Hence, while operating under the same conditions of the floor and head, all geometrically similar machines have the same specific speed, irrespective of their sizes. The specific speed can be expressed in terms of discharge for power absorbing machines and power or power P for the power generating machines. Specific power is referred as the ratio of power in or out of the turbo machine to its weight or unit mass or unit volume. Specific speed of a pump can be defined as the speed of geometrically similar machine discharging 1 cubic meter per second of water under head of 1 meter. Specific speed can be expressed for a pump, which is Ns is equal to N Q to the power of 1 by 2 divided by H to the power of 3 by 4. The specific speed of a turbine is defined as the geometrically similar machine which produces 1 kilowatt power under head of 1 meter. So based on this, we are going to derive this equation, that is Ns is equal to Np to the power of divided by H to the power 5 by 4. Here Ns is the specific speed of a pump in a power absorbing machines and turbine in power generating machines. So unit quantities are defined as in hydraulic turbines. It is usually to define the quantities as unit flow, unit speed and unit power, which are the values of the quantities under consideration per unit head. So we have to consider this in case per unit head. So unit flow is the flow occurs through a turbine while working under unit head. So unit discharge Q is equal to Q divided by square root of H. So where QU is the unit discharge or unit flow. Unit speed is the speed at which machine runs under unit head. It can be expressed in terms of NU. NU is equal to N divided by square root of H. Unit power is defined as the power developed by the hydraulic machine while working under unit head, where Pu is the unit power, which is equal to P divided by H to the power of 3 by 2. So if we are going to consider model studies for the prediction of model and prototype, we have to consider geometrically, kinematically and dynamically similar machines. So model is a small scale replica of the actual machine, and the actual machine or actual structure of the machine we call it as a prototype. So the geometrically similar machines will have a ratio of geometrical length corresponding to model as well as prototype will be similar, whereas kinematically similar machines for both model as well as prototype we consider it for velocity ratio which must be equal, and dynamically similar machines which will have forces, the ratio of forces for corresponding to model as well as prototype must be equal. So based on this, we have to define the model as well as prototype. So these are the references what we have to refer for Unit 1, that is Introduction to Turbo Machines. The Principles of Turbo Machines by D.G. Shepherd, and Fluid Mechanics and Thermodynamics of Turbo Machines by S.L. Dixon and elsewhere. And another textbook, that is Turbines, Compressors and Fans by S.L. Turbines.